Hello everybody and welcome to this series on logic and proofs, a guide to proof writing. I'm your presenter Udurilen Turisane, and these presentations are brought to you in association with ISFAP, the UKSASA Student Financial Aid Program. Since this is the first video and a bit of an introduction, we will give some motivation to the series. Why study mathematics? Since we're all math students and we're studying maths, well, we should give a little motivation. There are a bunch of reasons to study mathematics. You have to, one of the worst reasons, for interest's sake, or for its usefulness. Usefulness seems like the most reasonable reason to study mathematics. For instance, if one has some money or financial problems, the future value, present value formula might come in handy. Or if one has some sort of distance problem, trigonometry might be of use. Some more advanced applications include the application of linear algebra in modeling, calculus in engineering problems, and the use of measure theory in many problems involved in the financial industry. But what about proofs? We have the results, they're true, why not just use them? Additionally, what is proof? Why should we prove? To prove or not to prove? That is the question. For this, we're going to take some inspiration from A Brief History of Infinity by Brian Clegg. Infinity, what better and more abstract concept to inspire us? In this book, three approaches to infinity are distinguished: practicality, usefulness, and the great game. Practicality refers to those mathematicians who decided to use the mathematics they could see, systems such as the natural numbers, the real numbers, and the rationals. These mathematicians basically dismissed the idea of infinity. Usefulness. This refers to mathematicians who used infinity to solve their problems. They didn't really care about the debate of is infinity real, is it not, as long as the concept helped them solve their problems. And then there is the great game. These were mathematicians who were interested in doing mathematics for mathematics' sake. They didn't really care that infinity was not really a number. It was interesting and worthy of study as a concept in itself. We know how history went. The practicality approach lost. So let's have a look at the other two. Usefulness. Quite easy to understand. You have a problem, you develop a theory, and you hopefully get a solution. For instance, here we have a man with distance issues, as man has had throughout history, and thus we developed the theory of geometry, which we can use to solve our distance problems. The great game, the more abstract approach, and the game we are out to play. But why even play? Certainly, no one is going to request a proof of the Bolzano-Weierstrass theorem while you're out working in the fields. Well, why play any game at all? Poker, chess, etc. Let's take poker as an example. After many games of poker, you may find yourself quite good at making statistical decisions in everyday life. Seeing parallels between strategies employed in the game and the problems such as managing your portfolio and how much life insurance to get. And it's a fun game. And perhaps this may be true of the great game. Let's get proving then. Our first order of business is to find out what a proof actually even is. For this, we consult the internet's first stop, Wikipedia. According to Wikipedia, a proof is sufficient evidence or sufficient argument for the truth of a proposition. The concept applies in a variety of disciplines, with both the nature of the evidence or judgment and the criteria for sufficiency being area dependent. So, sufficient evidence or argument for the truth of a proposition. Thus, we need to know what a proposition is. Our propositions will be the statements that we, hopefully, aim to prove. Evidence and arguments. What exactly counts as evidence or argument? And sufficiency. We can have an argument with very little evidence. That doesn't actually help us. So, how much evidence is really enough evidence? And now, our discipline. Clearly, in our case, our discipline is mathematics. So, what is mathematical evidence towards the proof of a proposition? And more importantly, how much evidence is enough? So, let's give this a try. A first attempt. Here we have a friend, let's call him James, and he says, I have combed all of Europe and found nothing but white swans. Huzzah! All swans are white. So as James's proposition, all swans are white. Here James gives another proposition, a more mathematical one. He says 1 plus 1 equals 2, 1 times 1 equals 1, 2 plus 2 equals 4, 2 times 2 equals 4, and we notice that this actually gives the same answer, and so on until we get to 1 million plus 1 million gives us 2 million, and 1 million times 1 million gives us 1 billion or a trillion if you're using the American system. And James gives us a second proposition which says the only whole number x with x plus x equal to x times x is 2. So we have two propositions under our belt. Not bad. Now, if you clicked this video, unlike James, you are probably not spitting propositions and proofs for the fun of it. Your proofs are to be held to some standard of sufficiency by someone, probably your lecturer. Since we don't have anything to submit right now, let's let James submit his two propositions. And our propositions are not approved. Unfortunately, in the case of proposition 1, not all swans are white, as Australia does have black swans. And there exists another whole number, not 2, such that x plus x is equal to x times x, namely if x equals 0. This series, we are in the discipline of mathematics. We wish to develop a series of propositions about our subject or subsubject, backed by sufficient arguments to establish their truth. So, this goes back to what is a proof, what counts as a proof, and what is sufficient evidence for a proof.